The first regular paper is by Ji-Won Park, who's here to present, and it's BumpyPatch, Heightmap-based outdoor point cloud segmentation to find less bumpy roads. And she's from Kyung Hee University in Korea. All right. Go ahead.
Good afternoon, everyone. Thank you for being here. Today I'll be presenting our work titled BumpyPatch, which addresses the problem about accurately assessing ground texture in outdoor environments. My name is Ji-Won Park, and I'm a senior student of Kyung Hee University, South Korea. My research focuses on enhancing the navigation systems of autonomous mobile robots using artificial intelligence in the region of point cloud processing. This is my graduation thesis, and I wrote this alone with my advisor, Dr. Hwang. Autonomous mobile robots are increasingly operating in diverse settings, from controlled indoor settings to unpredictable outdoor terrains. These varied conditions present a significant challenges for the safe and efficient operation of the robots, as they encounter a variety of surface types, from grass and mud to concrete and bricks. This diversity in terrain presents a substantial challenge, the necessity for an adaptive control strategy that ensures vehicle stability and operational safety, particularly when they carry sensitive cargoes. The context of our study lies in understanding the limitations of current navigation technology in outdoor environments. Traditional methods of terrain classification, often binary like traversable or non-traversable, fall short in addressing the complexities of our outdoor landscapes. These methods lack the nuanced approach required for accurately assessing varied ground textures, which is essential for making informed navigation strategies. Our research builds on the premise that a more sophisticated method is needed, which classifies the ground multivalently. In our research, we've developed an approach to enhance mobile robot perception system through the assessment of terrain textures. A key aspect of our methodology is in the use of height maps, which are derived from 3D LiDAR acquired point cloud data. Height map is a grayscale image. In this image, varying shades of gray represents different elevations in terrain. By transforming LiDAR data sections into height map patches, we enhance the integration of advanced image classifiers for more efficient texture classification. This leads to faster and more dependable decision-making for robots in varied outdoor environments. Moreover, our height map methods is compatible with the gazebo simulator of ROS. So in a nutshell, the goal of our research is to determine the roughness of the ground surface to enable the outdoor mobile robot to find a road that is less bumpy. Below are the keywords. Let me start with the framework overview. We categorize scenes into static and dynamic types. This was crucial because we noticed that in real-time datasets like ROS-backed data tends to be sparser and is far from the sensor. This is called sparsity issue. This makes it difficult to accurately assessing ground plane. Therefore, completed point cloud scene and real-time point cloud data needs to be processed in different ways. So what is the difference between static and dynamic scene? A static scene is like a complete picture, uniformly dense scene that comes from thoroughly scanned LiDAR data. On the other hand, a dynamic scene is more like a series of snapshots that comes from a ROS-spec files, and these can vary in density and don't always give a full view. Due to those differences, we applied distinct segmentation strategies for each scene type, leading to the creation of height maps in different configurations. In this section, we will outline the pipeline of static scene analysis. We divided the point cloud data 3 by 3 meter patches, and each patch was transformed into 15 by 15 pixel grayscale height map. And the next step is to classify the height maps based on their imagery texture. In the case of the height maps, roughness refers to the variations of the brightness. We measure the roughness by observing how points are distributed in the surface, either scattered randomly or arranged in a straight line, or flat patterns. When I set the environment using Heightmap in gazebo simulation program and let the robot move on the ground and measure the value of IMU, inertial measurement unit, which represents the move of the robot. Through a series of repeated experiments, we were able to determine which Heightmap configuration indicates rough terrain. And this is the final result of the static scene. Red represents non-traversable area. Orange indicates roads that are passable but quite bumpy. Green signifies roads that are slightly bumpy, and blue denotes the flat surfaces. You can see these sections are well segmented in the point cloud file. And for the dynamic scenes, let me start with the off-road dataset I used. Rally's dataset is collected at Texas A&M Rally's campus, and this dataset, featuring LiDAR scans and images from a Husky robot equipped with Velodyne 3D LiDAR, offers a diverse range of off-road environments. And to handle the sparsity issue that arises when dealing with real-time point cloud data, we adopted a polar grid approach by dividing the point cloud into multiple bins as illustrated in the video. Next, we used PCA, Principal Component Analysis, to determine the traversable roads by analyzing the normal vectors of each patch. While there are numerous sophisticated methods for identifying traversable roads, we considered that determining traversable road is less crucial problem for our purpose, so thus applied a simpler approach. And when dealing with dynamic scenes, we tested two methods. One is a filter-based approach, which involves applying Gabor filters to cluster patterns. 3D LiDAR sensors on a flat surfaces typically shows regular striation patterns, showing like this. We applied various angles and frequencies of Gabor filters to the height maps, extracting these striation features. The number of the striation was then counted and clustered using the k-means algorithm. And the other is learning-based methods that uses DNN model. In our learning-based methods, we leverage semantic annotations from the point cloud data that Rally's dataset provides to construct the training dataset. The dataset includes varied categories like mud, puddle, or grass, and we selected the most frequent annotation in each grid to represent the value of each Heightmap patch. These patches then form the foundation of our image classification model, designed to accurately classify different ground textures. We use MobileNet as a model, and the criteria distinguishing annotations are as follows. And final output comes from these steps. And let me show you a detailed view. This is the result of the static scene. You can see the point cloud patterns are segmented by its roughness. And this is the result of the dynamic scene through RVs. The processing speed is average 3 Hz, but the speed can be faster, depends on the computational environments. And the key experimental results is like this. Terrain characteristics for each classification results. There are various methods to measure the roughness, but among them, I used variance in Z coordinates and residual in Z coordinates. From the experimental results, we can observe that in all data sets, the classification was effectively aligned with the roughness of the terrain, where class 0 represents flat surfaces and increasingly rougher roads are indicated by higher classes. So concurrently, both the variance and residual values increased as we move from class 0 to the rougher classes, indicating the correlation between these metrics and the terrain's roughness. Class 0 has the most uniform terrains with the smallest Z variances and residuals. Meanwhile, class 3 features the roughest surfaces, with highest z-values. It is the same in the dynamic scene as well. And we compare the filter-based methods and learning-based methods using the rallies dataset. And these results reveal that while both methods effectively categorize the terrain roughness, the learning-based approach was more precise in distinguishing different terrain types, as evidenced by the clearer variations in z-value and residuals across the classes. And lastly, but not least, we compare the computational efficiency of Heightmap-based methods to the traditional point cloud-based methods. The result shows that the Heightmaps required significantly less processing time and memory in both static and dynamic scenes, demonstrating their efficiency in terrain analysis for autonomous navigation. Ultimately, based on the classification results, our goal is to develop a navigation system that seeks less bumpy roads, thus completing the outdoor mobile robot system. This approach can apply not only in the outdoor environments like farms, but also a planetary explorations rovers such as those used in the Mars. And thank you for listening. The source code is open. You can access through the QR code.
Eric had to step out, so he asked me to do the timing. That was incredibly disciplined. You were on time.